the standard deviation for like the XP.
So remember that. You don't have to remember this. I put it on there. And that, of course, is a formula for the what? Variance. I love it. You just take the square root, get the standard deviation. What do I need? I need a column of x squared p of x's so I can add them up. Right? You cover up the summation, you see what you need. Why do I not need this in there? Because it's minus, that's a separate term. Good old order operations. Please excuse my dumbass son. You got to do this stuff first, and then you can subtract the mean squared. So our normal table starts off like this, and then of course we add one of these. And that's so we can get the what? What do we get from this? The mean. Yeah, the mean is the sum of x p of x. I love it. Some of you guys are like, wait, there's no, well, yeah. So no. That's what you do to get the mean. And then you just need one more column. What I normally do is just multiply these together. Or you can square this and multiply to this if you want an extra step. And then you add that up, and whatever number you get, you're going to put right here. Bam. And subtract the mean squared. That's the variance, take a square root. Is that cool?
So it just was a square root.
What's that?
So once you get the variance, you square root. No.
Yes. Cool. I like it. Now again, I really remember where this came from. Some of you guys decided to use the original formula, which I said I have no problem with. It's a little bit more disgusting. It still works. Of course it does, because that's the original formula. That's the same formula. These are the same. These are the same. I showed you the first couple steps of this that leads us there. Yes?
What were you looking for element 1A?
Oh, yeah, well, so like we said several times, and like so on that handout on both sides, what two things have to happen for it to be a valid probability distribution? All the probabilities have to be between 0 and 1, and all of the probabilities have to add up to be 1. Now, if you say this, and you think I'm being picky, no, I'm not. You got to mean what you say. If you say 0 less than x less than 1, and I see 5, 6, 7, 8, I'm like, what kind of stuff are you on? None of those x's are between 0 and 1. You're not talking about x's, you're talking about probability of x's. And don't look at me and say, you know what I mean. No, I'm not going to make any guesses. You're supposed to show me what you mean, right? So what's this supposed to be? Two things, actually. So all the probabilities have to be between 0 and 1. They have to add up to be about 1. There might be some rounding stuff in there. I like it. Cool. Okay. Anything else from the quiz? Any questions from that last quiz? All right. Before I lose any more of you, I guess everybody who's left didn't need this. Here's your practice test.
When's your test?
Yeah, when is the test?
On Monday?
Yeah, a week from today. Just remind you guys, you all know all the dates of everything shows up on the syllabus. You got a homework sheet, right? Yes?
When are we going to get what we have?
To be honest, I normally don't do that till after the second test. So I'm pretty well right on schedule for that. As always, you can come by my office whenever you want to and find out what your score is. I don't care if I sound old-fashioned. I probably do because I am.
You can't tell us.
Of course I can. Of course I can. If it's the email that I have on file for you, right? I don't want to give your information out to somebody who isn't you. Even your parents. I love it when I get a phone call from a parent. I'm like, you're a parent. Leave me alone. I don't teach high school. Ha. Ha. Thank the gods. Okay. So I'll have the answer key for the practice test, obviously, on Wednesday. I like it. So, let me tear your attention away from that. Yes?
I think every project is.
Oh. I'm evil. Nothing there for you guys. All right. So let's get back to where we were. Let me start off. Let me see. Why don't we do this? How many of you guys? Let's see. Well, let's go ahead and do this. If you don't have a calculator right now, I want you to pair up with somebody who does. And then, so do that. Who does not have a calculator? All right, now put your hands up. If you don't have a calculator, okay, now find somebody near you that does. There you go. Now get close to that other person. Oh. All right. So is everybody? Anybody want to help Carmen out? These people, okay. Those people look like they could help you. All right. And the rest of you guys, if you want to team up with somebody, you can. All right. Start off easy. All right, so that's just like what was on the quiz. So find this, and then all right, those two problems. So we really only need a calculator for that second part. Well, obviously, I just quizzed you on this stuff. I want to kind of also, on the back of that, go over a couple examples, because we're going to build on this today with what we did last time. I'll have to remind you what we did last time, too. Who's got this first one done? How do you find this? You should draw the picture for yourself. Kind of gives you a visual idea of how big your answer should be. So it should be relatively small. And what do you guys, when you look up 3.01 though, what do you get?
0.9987.
Of course, that's on that side. You immediately put it on that side because that's what the chart tells you. And you try to be nice to yourself. Let the math itself be the hard part. Areas below z-scores go up here. Z-scores go down here. We want that area, so it's going to be, 1 minus this. So 0.0013. Some of you guys might use the shortcut. So if you look at negative 3.01, you'll get the same answer. I like it. Cool. So to be beyond 3 standard deviations, it makes sense. We should know by now that that should be really unlikely to be more than 3. Because when does unusual start? After 2 standard deviations. So this is somebody who's like more than 3 standard deviations up on height. How tall would they be? They would be stupid tall. What percentage of people are up there? About 0.13%. Right? This is the top 0.13% of height. Okay, I like it. We need to redistribute some of that height to some of us people down here. That's right. Now, how about this guy? What's the difference between these two? They're both normal distributions. What does that word standard normal distribution mean? Standard. And that's the key difference between these two problems. Yeah, standard normal distribution means there's z-scores. The mean is 0. Standard deviation is 1. They've already been changed into z-scores. So I just need the chart directly. Over here, I know it's normal. It's not standard normal because the mean isn't 0 and the steps aren't 1. So I have to force them to become that way. So first thing I got to do is do what? Draw a picture. Oh, yeah. Draw a picture. What goes in the middle? 30.1, I like it. And here's 28. Here's 30.5. Not drawn to scale, but I don't care. See, when you do this, now you know that z-score should be negative. That one should be positive. I mean, when you do the visual, if you understand what you're looking for, it will help you. I'm trying to force you to help yourself. So what do I have to do now? Yeah, make both of these into z-scores. So I have to do 2 z-score formulas. I love the person that tries to do 28 minus 30.5. That doesn't make any sense. Z-score formula that I erased already has to be minus the mean. It's got to be. So I got to change each of these. So 28 minus the mean divided by standard deviation. And 30.5. What the hell is that, child? 4.98. Playing Goat Simulator. There's a game called Goat Simulator, in case you didn't know.
Yeah.
Yes, okay. The mods, of course, are interesting, as always. I like how some of you guys really perked up when I said. So, change each of those to z-scores. Now, I can always make a z-score. I can always make a z-score if I know what I need. But what is it that allows me to use a z-score chart with z-scores is if I know it's normally distributed. That's the key. I can make a z-score out of it. If I know the mean standard deviation, I can make a z-score, 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 yeah. But I can only directly translate them into probabilities right now if I know that it's normally distributed. It's the only thing that chart works for. I like it. So I don't know. Did you guys do this one yet? 450. That's like 0.08. So round it to 0.08. And then this one, I don't know, 2.1. 42. What is it? Negative 0.42. It's not too hard because the bottom's almost 5. So you just double the top and then scoot it back once. Anyway. So now I can look up negative 0.42. I can look up positive 0.08. What do you guys get when you look up positive 0.08? .7881. And then we look at negative 0.42. 3372.
The first one is 5.
0.08.
First one's
Should be 0.5 something. 0.5. 19. I love that. Anyway, sorry. I love just taking an answer and going until somebody actually checks it. I love it. So that's good to know that somebody's actually trying to do it themselves. And then negative 0.42, what do you get for that now? 3372. This is what somebody else told me. I like it. Please don't feel bad about making a mistake. Like you probably look at 0.8. Or your eyes go to the next row. It's kind of sucks. I try not to take too many points off for those kind of things. Those are just little derpy things we all do. And now you find the area I want. Subtract those. I love it. All right. Please, dear God, let this be easy. Right? I mean, and the whole other level of this that we're working towards is we're trying to get enough basic abilities down so we can really start to tackle a real problem. A real, situation where we need to apply some of this analysis. You just need to know how the heck these things work before you can get there. So what do you get when you subtract those? 0.1947, okay. Or almost 20% chance that somebody would be between 28 and 30.5, whatever this is. I like, yes. If you want to. Either way. Because when I see those, they're the same damn thing. But they're just different representations for the same thing. So if I don't say, and I never will, besides rounding issues, if I don't say what form to put it in, you can put it in either one. Okay, I like it. As a human, we like percentages better. That's why we made them up for ourselves, because we knew we'd like them better. All right, so to add on the extra layer to this, we got to go back. This is what I call your classic z-score problem, right? I give you an x score, you make it a z-score, and you look up the percentage. Okay. Now we're going to tweak this a little bit. Right? There's going to be a tweak to this, and it's going to be a tweak to some stuff later, too. This is the first tweak. We got this here. So last time we talked about fictional Florida, and I had an age distribution look something like that. I don't know if you guys remember this. This is after I talked to individual people and plotted their ages. And then I can calculate using chapter 2 stuff. I can calculate the average. I can calculate the standard deviation. Okay. But, again, in statistics, we normally do not take a single thing. If I wanted to test a claim, so let's say somebody's claiming that they can measure out on a board perfectly 4 feet. Just looking at they can always measure exactly 4 feet. Are you guys with me? Or, close. They're like really close to 4 feet. So, if you wanted to test their claim, would you just look at one time that they do that? Or would you look at several times that they do that? Several, because that one time could be either they got lucky, if they get it right, or they were really unlucky or something. They had to cross eyes, and they got 4.5 feet. They're like, oh my God, let me do it again. If you did it 80 times, and 80 times they got 4 feet almost perfect, except one time they got 4.5 feet, you go, all right, that's freaking 79 out of 80. That's amazing. Do you guys understand what I'm saying?
Yeah.
Okay. All right. I didn't really say anything too crazy yet. Right. Okay. So in statistics, what we're working towards right now is the ability to test a claim. And that's, of course, where statistics is used all the damn time. This is where you guys come across it. It's been clinically proven. What the shit does that mean? That normally means in the correct conditions, controlling the right variables, using statistical analysis methods, we've come to the decision that this actually does something, right? This medicine works better. You guys still with me? Why is everybody looking at the floor? What's happening?
We're tired.
Okay, worked through it. I'm doing the same thing myself. So this is the picture for one thing, and I have to be really lucky to have a population that's normally distributed already. So like heights or SAT scores, very, very specific situations, do I have normal distributions already? So this is the first kind of step into, well, what do we normally do? Take samples, and how does taking a sample affect the end picture? This is me plotting individual people. So that right there, that would be 65-year-old Merle down in Florida, right? And so forth. Every little point is a person. So now I say, let me take 20 people at a time. So now it's going to look a lot more like this. Because, just to jump to the conclusion here, bless you. Because what's going to happen most often is I'm going to get a mixture of people. That is the most likely thing. It's some kind of mixture of people. Are you with me? Is that more likely than getting a bunch of people just from one clump? Yes, of course. The most likely thing is a mixture. That's why the middle is now the tallest point. The mean stays in the same place. What the hell does that mean? This means the mean of the sample means. Because what am I plotting now? I go up to 20 people, and I say, figure out your average age, and then tell it to me. So they tell me 11. I'm like, let me do that for you. Probably not 11. So I get their average age, and I plot it. So this point is no longer Merle. That point is now Merle and 19 other people that I randomly picked. That is their average age. So do you think, would it really freak you out if you went out right now and randomly picked a person and they were over 60?
Yeah. No.
Well, all right, if you're freaked out by old people, then yeah, I guess so. But relative to, would it freak you out if you went out and picked 20 random people and their average age was over 60? Yes, that would freak you out a little bit. 20 random people and their average comes out to be more than 60, that's a little bit freaky. Why is that freaky? Because if you take 20 people, you expect their average age to be close to the actual average age, right? So if we're taking it from Grossmont College, it should be in the 20s. You guys understand? So it has nothing to do with you personally, right? It just has to do with any random selection should be close to the population statistics. That's the whole idea of taking a sample. Now, is it impossible that I go out and pick randomly 20 people and their average age is more than 60? Is that impossible? No. It's just really unlikely. Is it impossible for me to put a quarter in 3 machines in a casino and then win all 3 of them? Is that impossible? No. Is it likely? Oh, hell no, right? All right, maybe. Okay. So what happens here? The mean stays the same. The mean of the sample means is the same as the mean of everybody anyway. Just because I take people 2 or 3 or 20 at a time is not going to change the average age of Florida. I can't. But what happens to the standard deviation? What does the standard deviation tell you? The average distance from the mean to the data points. So which one is, on average, further away from its own mean? The first one. I like it. Now I made this one taller. I should have the same view. Oh well. This standard deviation is smaller. This one, the standard deviation of the sample means, is less than it used to be. Didn't the picture just go like that? Go in. Yes. So standard deviation is a measure of how far you get away from your own mean. Where are most of the sample means? On the mean. So they're all going to be 0 away from themselves, right? They're going to be 0 away from the mean. Stay with them, please, dear God. Tell me everybody understands. This standard deviation is smaller than this one. Yes, okay. You got to know that. We've known that for a long time. This is the kind of picture I showed you before. Okay. And here's the magic number. Once I hit 30, or greater than 30, let's stay with the book, n greater than 30, I become normal enough. Sounds like the right kind of phrase to describe me. So once I get a sample size greater than 30, the resultant picture of all the means becomes normal enough. What do I mean by normal enough? Normal enough to use the chart. Okay. So this chart has a bunch of answers just waiting. But in order to use this chart with all the answers that are just waiting, I need a normal distribution. I have to be really freaking lucky to have the thing just start off normal, to be honest. So what do I then have to do? I just got to make sure that the samples I pick are more than 30. And then I know I'm working with a normal distribution. Now, does that make any kind of sense? I mean, you're going to get more things in the middle, which means it's going to start low, go high, go low. And it's going to smooth out as you get larger and larger sample sizes. Things are going to smooth out more and more and more. Once you get above 30, everything's beautiful. If you start with something that's already, if you started with a uniform distribution, you might just need n equal to 5 to get normal. If it starts off pretty in some way, it won't take as many. But what do we always have to think? We always have to think this, just to cover our ass. If we don't know what it looks like, we got to say this. All right, now, I don't know if you guys remember this, but the only new thing, the only real new thing out of all this idea is that the standard deviation is smaller than it was. In fact, it's equal to the old one divided by square root of n. As n gets bigger, I go more and more towards the middle. Is it more likely to pick 20 random people and their average age be more than 60? Or 80 random people and their average age be greater than 60? Holy shit, the second one is like crazy, right? So as I pick larger and larger sample sizes, everything goes towards the middle, leaving less stuff out there. More stuff inside. Standard deviation gets smaller. I love it. Okay, so what does this mean practically? What does this mean nuts and bolts to you? Okay, here's what it means. So let me put all this down. Let me kind of make this 1, 2, 3. I can't remember if I said the name of this thing last time. This is called the central limit theorem. Central limit theorem. Or chicken, lettuce, tomato is what I was thinking. Central lettuce theorem. Central lettuce theorem, I like it. Okay, so if you see reference to the central limit theorem, which is chapter 7, then that's what it's referencing, is this idea. Okay, I like it. So, let me give you 2 situations here that this comes into play. 2 kind of problems you'll see from me. Let's see. We know sigma equals 11 and mu equals 290. We take a sample of, what you got, Jeff? 42. Find the probability that the average is less than 285. So what is the sentence up here that allows me to do the probability work that I have to do? Yeah, because the sample size is 42, which tells me what? Normal enough. So n equals 42 greater than 30, normal enough. If I would have said 27 there, you officially would have been unable to do anything. You just sat there like, or whatever face you want to put on. But now we can do something. Now, so I know it's normal enough because the sample size is big enough. Before I start, the very first thing I should do before I draw a picture or anything, what should I do? When does this have to happen? When does this have to happen? When I take a sample and I ask about the sample mean. Right? So I took a sample and I'm asking about the sample mean. So that means the standard deviation's got to change. What am I looking at now? The probability that the sample mean of these 42 is less than 285. Who am I comparing this one sample of 42 to? All the other samples of 42. And what is their standard deviation? It ain't this right there. It's not 11. What's that for? What's this for? What does standard deviation tell you? Average distance from the mean to the data points. I like it. And in this case, these are the individuals. This is the individuals here. This is how spread out the individuals are. Okay? Let's make this age of children at playground. So on average, they're 11. Oh, crap. That's the standard deviation. 290 years old. Maybe not 290 years old. Let's see. Yeah. Age of children at playground in months. There you go. Does that make it better?
No.
12 goes in there. That's still kind of old, isn't it? It's like 20. Screw it. All right, let's say 209. Age of turtles. No. Sure. All right, just to give it something. We take a sample of 42 turtles. Find the probability that the sample mean average of those turtles, sample mean of those turtles' age is less than 285. So, anytime I take a sample of stuff, so here I got a sample of turtles, and I'm asking a question about the sample mean, who am I comparing these 42 turtles to? All other groups of 42 turtles, right? So, the very first kind of z-score problem we did, like earlier today we did some z-score problems, I was talking about picking one person or one thing. What's the probability they're here or there, or greater than this or whatever. So this is a picture of individuals. That is the standard deviation for the individuals. In fact, on your calculator, what does this look like? It doesn't look like this. It looks like that. And what does x mean? Each individual value. So now this notation here makes even more sense when you realize what the calculator does. It says here, this is the one for individuals. This is the one for groups with means, right? So in order to do this problem, I got to make the z-score, but I got to use the right standard deviation. I got to use the one that works for groups of 42. Does 11 work for groups of 42? No, that's individual variance, right? I need the one that works for groups of 42. So what do? So you get the new one, take the old one, divide by square root of n, so that's going to be, the old one was 11. N is 42. What that is, 1.77? Is it? What do you guys think? 1.697? 697 what? 3, okay, I like it. Alright, and then you just do the problem the same way you always would. The minute you do this one thing, the problem becomes old-timey problem. What do I mean by old-timey problem? I mean, you draw the picture, you make a z-score, and you look it up. What goes in the middle? 290. And I'm interested in 285, specifically less than. You make that into a z-score. What do I put on the bottom? Yeah, the correct standard deviation. So I'm not talking about individuals, I'm talking about groups of 42. Well, there's the spread for groups of 42. It's that simple. The concept is kind of freaky. And I got to show you some pictures, and I got to give you the handout from last time, shows a concrete example. But the actual practical nuts and bolts that happens to you is very minimal. That's the only new thing. So don't divide it by 11, you divide it by 1.697. I don't know. Negative 0.31. I'm making shit up. Negative 2.95. I like it. That's a z-score because you told yourself. The people that do this drive me crazy. And then they put 2.95% or, I don't know. Tell yourself what the hell you're doing. It's a z-score I've got. That's a z-score. And the question, what's the probability? Oh shit, I'm not done. Look that up and what do you get? 0016. I like it. It's a very small chance. I like it. All right, so let's do another one together, and then I'm going to give you guys several to try on your own. Okay, now watch. Oh, let's see. I could get myself in trouble here, but too bad. Let's see. Okay, so know that the average height of first graders on some island off the coast of the U.S. In case I'm really far off. It's 35 inches with a standard deviation of 3.17 inches. Heights are normally distributed. Okay. A. Find the probability that find if we pick one first grader from this island, probably that their height is greater than, what you got, 37 inches. B, find if we pick 16 first graders, the probability that their average height is more than 37. So part A and a part B. You guys just got to take my word for it.
Heights are normal what? What does it say?
Normally distributed.